Okay, so we just talked about our crisscross rule. Now we're going to be talking about transition metals. It's what we've been skipping. We've been skipping the transition metals. But they're elements too. They're all in nature. We have iron, gold, some of the most memorable metals ever are transition metals. So let's make sure we know how to name them too. Now, the rules are going to stay the same. Thank you. Just how you find the charges are going to be different. Let's put transition metals. Transition metals. Now, when we talk about transition metals, we're going to be talking about group 3 through 12. And we're also unfortunately going to be talking about some of these too. They're the post-transition metals. They also have a variety of different valence electrons. Okay? So the post-transition metals are, luckily, gallium, germanium, indium, aluminum. They always have those charges. Those post-transition metals are meh. Just look at the chart. Now, when we're looking at this, okay, we're discussing this, we're going to try to name them. We will always use Roman numerals to indicate charge. Roman numerals to indicate charge. Okay? Always use Roman numerals to indicate charge. So let's say, for example, Mr. Winston or I give you a fun little problem like Fe 3 P 2. We would expect you to name this, okay? We would say, okay, I gave them Fe3P2, so now I expect them to name it. Now, if we name it like a salt, we just have to find it on here and be like, okay, we got iron. Let's put iron here. Iron, we go to P, we go, oh, look, it's phosphide. Iron phosphide, easy. I'm done. Here you go, Mr. Curlin. Red band. Nope, it is not iron phosphide. And unfortunately, it's not iron phosphide because iron can have multiple different valence electrons. Just how it works. It's sitting, if you remember, in the d orbital. The d orbital has a lower energy level than its corresponding s orbital right next to it, but it still interferes in weird, messy ways. So you'll probably, when you're dealing with this d orbital, you might only have the two. So the s, this will be your valence electron shell, the last energy shell. So let's say we are looking at iron. Now iron will still have this s orbital. It's your last energy level. But right under it is this d energy level, which starts here at scandium. Now, because it starts right here, it can give a messy amount. And that's because sometimes they pop up, sometimes they don't. It's just, now let me draw this so it makes more sense. Transition metals have a messy amount of valence electrons because, let's look at potassium. Potassium's valence electron shell is this fourth shell, okay? It's an s orbital, so it looks like a sphere. And that's where its one electron is. It's just floating somewhere about in this cloud. And remember, this electron, it's moving at lightning speed. Everywhere. It could be anywhere in this s orbital. Now, when we add, let's say, calcium, it gets a second electron somewhere, bouncing about everywhere. So we always know potassium and calcium's valence electrons, how many they have. Now, scandium. Scandium, you start with a d orbital. So this is a d orbital. All of our d orbitals are actually on a lower energy level, so they're not as active. So we kind of picture that as being under this cloud. So they're not actually reacting. So you have maybe this d orbital somewhere, and whatever it looks like, I don't know what this looks like, is somewhere inside the cloud. But unfortunately, sometimes these can pop out. They can be like, oh, I am reacting. These little clouds, and they actually do this reaction because this is my 3D orbital and this is my 4s. 4s is that outermost energy level, but 3D can make things messy. So here, our next one, scandium almost always does 3+. It's just, but luckily this little piece that pops out always gives us an electron when it reacts. But titanium can either give that one spot, so there can be an electron up here, or there can be an electron over here. But sometimes there's not. Sometimes it doesn't actually react because it's hard to find. It's hard for that other atom to pull away because sometimes it's inside that energy level. It's not as reactive. So that's why our transition metals aren't always as active. So let's actually go back to naming them. That was just a side thought. I like understanding visually why things work. I think it's important. So here we have iron 3. Well, sorry, iron 3p2. Phosphide 2. So how do we name it? We are going to name it based off the charge. Now you're going to ask me, Mr. Curlin, how do I find the charge? I'm going to say reverse crisscross. Reverse crisscross. Let's not do this. Crisscross. So here, previously, you went from top to bottom. Now we're going from bottom to top. So we have Fe3P2. To find the charge, just go backwards. Boop, boop. So we know that iron's charge is 2+. And we know phosphorus' charge is 3-. And we can check that real quick. Does phosphorus have a 3- charge? Oh, it worked. So we know that iron is going to have a 2 charge. Now, this in the Roman numerals indicate this. So to name it, you're going to say iron. Oh, what's my charge? Oh, 2. Phosphide. Now let's go backwards. I'll be back with more paper. I ran out. So let's go the opposite direction. So let's say I give you platinum 2. I always misspell this dang word. Platinum 2, let's react it with bromine. Now, this is actually easier than its sisters because you don't even have to go to the periodic table to find it. We already know its charge. Boop, boop. So we're just going to do the crisscross rule again. We have P2, 2+. We know bromide, if we go to this periodic table, sits at 1-, Br, 1-. We're going to crisscross. We're going to be left with PT1, Br2. As always, get rid of the 1s, and we're left with PT, Br2. And that's how you not only name ionic compound transition metals, but write their formulas.